We already know how to compute this integral from Calc 2. You should recognize that the integrand here, 1 over 1 plus x squared, is the derivative of the arctan function. That's no problem, right? We do the usual thing. We really take limits here. You should know that as x goes to infinity, arctan goes to pi over 2. And similarly, we'll get a minus pi over 2 on the other end. Pi over 2 minus a minus pi over 2 gives us pi. What if you didn't know that? Well, we also employ a very clever substitution here to do this integral. 1 over 1 plus x squared dx. If you just set x equals, say, tangent theta, then you'll have dx equals secant theta, secant squared theta d theta. And now you just do the replacements here. So this becomes an integral in theta now. Dx is secant squared theta d theta. And on the bottom here, I'll have 1 plus tangent squared theta. And my limits of integration, well, it's just the same from the above. Theta goes from minus pi over 2 to pi over 2. But what's 1 plus tangent squared theta? That's just secant squared theta. And so this just really becomes the integral from minus pi over 2 to pi over 2 of just d theta. And surprise, surprise, we know how to do this. Pi over 2 minus minus pi over 2, that's just pi. Again, what if you didn't know that? Well, there's one last way you can actually evaluate this integral. Minus infinity to infinity, dx over 1 plus x squared. You can complexify it. In fact, we'll actually just use the magic of the residue theorem to actually evaluate this integral. So what we need to figure out is how to do this. So we'll look here at the upper half plane of the complex plane. This is the real axis, the imaginary axis. And let's imagine drawing a large circle, a large semicircle rather, oriented in the usual counterclockwise direction. Call the semicircle part here gamma sub r, because this is a semicircle of radius r. And now we just need to figure out some things on the inside here. Well, if you notice here, this function here, 1 over 1 plus x squared, does indeed have a pole if we complexify it. So we can write f of z as 1 over 1 plus z squared. And if we factor that on the bottom, we'll just get z plus I times z minus I on the bottom. So I have poles at both I and minus I. But I'm more concerned about the pole that lies in the upper half plane inside the semicircle. So we have a simple pole here at I. This semicircle encloses that pole. So by the residue theorem, this integral, which is really just a closed line integral from gamma sub r, and take the union of that would be the union integral minus r. The value of this integral is going to be 2 pi I times the value of the residue of f evaluated at the point I. And that's easy to find here. Since this is a simple pole, we'll just cancel the factor that is causing the problem and take a limit as z goes to I, but that's no problem. So this is 2 pi I times the residue, which will have as the limit as z goes to I, 1 over z plus I. We have no problem evaluating this limit. It's 2 pi I times 1 over 2I. The 2y is dropped, and I'll work with pi. But the problem is if we're not actually done. See, I evaluated this complex integral around the semicircle, but I really just want the part on the real axis. So notice I can actually decompose this integral into pieces. The integral over the semicircle and the part on the real axis is really the integral over the semicircle plus the integral from minus r to r. And here we're making the implicit assumption that r is greater than 1. So we need to actually show a couple things. We need to make sure that this thing on the left is equal to the thing on the right. We need to make sure that this piece here, this first integral here, actually goes to 0. And we'll employ the so-called Cauchy estimate to do this. So we look at the integral over gamma r of dz over z squared plus 1, and we'll employ the usual parametrization. We'll let z equal r e t I theta, And so now this integral now just becomes an integral from 0 to pi. Remember, we're working with the semicircle, so theta goes from 0 to pi. Now, this is the integral from 0 to pi. Well, dz is just IR times e to the I theta. On the bottom here, we'll get r squared e to the 2I theta plus 1 theta. Now, we can evaluate this integral if we want to, we can try, but all we're only concerned about is an estimate. So now we're going to actually estimate the size of this integral. So I want to look at the absolute value of this integral over the semicircle, dz over z squared plus 1. And actually use the triangle inequality to write the following. The integral from 0 to pi, and I'll have on the inside here mod I r to the ei theta over mod r squared plus, well, not yet, mod r squared e to 2I theta plus 1 theta. And now we can make some estimates here. The numerator is easy, okay, because I have an r here which is a real number. I can just pull that out as absolute value r. But now on the bottom, we have 1 over this thing here, mod r squared e to 2I theta plus 1. Well, if you know how to estimate this, this is actually no problem because it's in the denominator. We have to be thinking backwards. I want to make the denominator smaller to make the expression larger. And I can disregard the 1 here, the plus 1, to make this bigger. And I'll have this thing here left over, r squared to e to 2I theta. So this is less than or equal to r over r squared in absolute value. And then I'll just have 1 left over here. It's just pi in the integral. And the integral from 0 to pi of 1 to theta is just pi. And the thing is, if I allow this to go to infinity, if I allow r to infinity, this is actually 0. Why? Because I'll have mod r divided by mod r squared, that gets reduced to 1 over mod r. And r is in the denominator, I can let that be as large as I want. This integral is now 0. So, we know now that the limit, as r goes to infinity, this integral is 0. So we're safe. And what does that now give us? Well, we said here that the integral over the semicircle plus the extra bit on the real axis, dz over z squared plus 1, this was equal to pi, but this needs to also be equal to the limit, as r goes to infinity, of this bit here, the integral from minus r to r of dx over x squared plus 1. And of course, we took a limit in that first term, that goes to 0, and so now we have the value of the integral that we want in the arctangle. So this thing is now pi. One integral, 3 methods.